All right, so what we have here is an example involving special relativity. Now we have two objects, object A and object B, moving away from each other at 0.8 times the speed of light. The problem is to find the velocity of object B, taking A to be stationary. That is, what is the velocity of B if object A is the observer? Now, with a normal moving object, much less than the speed of light, let's say 8 meters per second. Say object alpha is moving 8 meters per second and object beta is moving 8 meters per second in the other direction, starting both from this point of origin here. We would see that the point of origin would appear to be moving at 8 meters per second and the object beta would be moving at 16 meters per second if we took object alpha to be stationary, 0 meters per second. But what would the velocity of object B be if both these objects are moving at 0.8 times the speed of light? The answer is not 1.6 times the speed of light. Relativity tells us that the maximum velocity we can observe is the speed of light. So we have to use these equations here. These are the Lorentz transform equations. X prime equals gamma times x minus vt, and t prime equals gamma times t minus vx over c squared. Now v in both these equations is going to be the velocity of our new stationary reference point, object A. So v is negative 0.8 c. Now, if we want to find the velocity of an object traveling at constant velocity, we don't need to worry about taking a derivative or anything with a constant velocity. We can just do x final minus x initial divided by t final minus t initial. And since we're traveling at a constant velocity, so we can basically choose any values of t we want. And x, of course, is a function of time. But to find v prime, which is our new velocity with our new reference frame with A as stationary, we have to do x prime f minus x initial prime divided by t prime f minus ti prime. So we have to find x prime and t prime for object B. Now, what I like to do is I like to use 0 for the initial time. It just makes things easier, and to use 1 for TF, the final time. And we're going to say that object B is at x of 0 at time 0. So we say that it starts at point 0. Now, x prime of t0, we simply plug 0 for t into our original equation up here. So t is 0, and we said x of 0 is 0. So we have 0 for x. So x prime equals gamma times 0 minus 0 times negative 0.8 c, because that's our velocity. Now t prime, again, is that equation right there. So we have 0 for time minus, and then we have negative 0.8 c for the velocity. We have 0 for x because at t of 0, we're starting at x of 0, and we divide by c squared, but this term's 0 anyway, so we're not worried, so 0. So x prime 0 and t prime 0 are 0, while x of 0 and t of 0. Now we have to find x prime and t prime when t equals 1. So let's go back up here. X prime equals gamma times x minus vt. What is x going to be? X is going to be our velocity times 1 second because we're taking t to be 1 second. Again, I said like using 0 for the initial time and 1 for tf. So we're plugging 1 into this equation here. But then we have to find x for b. And since b is moving at 0.8 c, it's just 0.8 c times 1. So 0.8 light seconds, 0.8 cs, minus vt. And v, again, is the velocity of our new stationary reference point A, which is negative 0.8 c. So it's 0.8 minus negative 0.8 c times 1 second. I don't know if you can see that. But then it's going to be 1.6 cs, 1.6 light seconds times gamma. That is x prime for 1 second. And what's t prime for 1 second? Let's go back up here. T prime equals gamma times t minus vx over c squared. So t is just going to equal 1. V is still negative 0.8 c because v in both these equations is the velocity of our new stationary reference point. X, we're looking at x of b after 1 second, so that's positive 0.8 c s, 0.8 c light seconds. Velocity is all in terms of c, so it's light seconds. And then we just divide by t squared. So let's go back here. 1 for t minus negative 0.8 c for v, 0.8 cs for x, because our point B is going 0.8 c, so times 1 second is 0.8 cs, divided by c squared. This should be 1 second s, 1s. So then our velocity is our t prime is gamma times 1.64 seconds. So now we have x prime for 1 and t prime for 1, which is gamma times 1.6 cs and gamma times 1.64 s. So this is, again, t prime, x prime, t prime. And gamma, we don't actually have to do out gamma, and you'll see why in a second, but if we do out gamma here, gamma is 1 over the square root of 1 minus v squared over c squared. We just plug in all our terms, and we find that gamma is 1.67. But we're going to be dividing those terms out anyway, so we didn't even need to solve that. But we're finding v prime for b, which is xf prime. Yeah, I already went over that. So xi prime and ti prime were both 0, as we found, just like x initial was 0, t initial was 0, and then x prime initial was 0, and t prime initial was 0. So the new reference frame didn't make any difference for the initials. But after 1 second, x prime becomes gamma times 1.6 light seconds cs, and t prime becomes gamma times 1.64 seconds. And as you can see, we didn't have to do out gamma because those divide each other out. And we find that our velocity, v prime, is 0.975 c. So if we take A to be stationary, we find that the velocity of point B, I didn't even write A and B there. We find that the velocity of point B is 0.975 c. So that does make quite a bit of difference compared to the regular motion, because with the regular motion with 8 meters per second, if both objects are moving away from each other at 8 meters per second, if we take that point to be stationary, it's going to be perceived as 16 meters per second. But with 0.8 c, the other object is perceived at 0.975 c.